Here is another teardown video. This thing is really, really big. Tunnel gun supply. And something about kilovolts and microamps. And then you can set the voltage, I guess. Internal or external control. And you can power off and on this section without doing it for this section, just individual. So here we have cathode current supply and then voltage and milliamps and a low and a high. See, it almost works. Some external pulse. Set the high and low current. So this is current level. How do you set the volts then, if this is current level? I have no idea about the range of voltages or anything. I don't know if this will blow up or if it's going to work. It was pulled out a trash can a long time ago. The internet does not know anything about any of the numbers or the names or anything. So that means this thing is very old. Maybe older than the internet. Let's look at the back. So this is the back side. Some current supply out. And the high voltage out, high voltage common, individual fuses, and this power inlet connector type is very, very old. And look at also all the screws, those are brass. So all these things tells me it's very, very old. And the top lid is one entire piece. So that means we need to open it from the bottom. So this is the bottom where we need to open. 2 screws here from the back. That should be fairly easy. And then look at this. One is missing. So there's a screw under the rubber feet. So that means, yes, the usual hide the screws trick. Some rubber stuff is pressed into aluminium maybe. So all screws are out. Okay, so it's behind the top. So, yeah, exactly what it was. Away we go. Wow, look at that. So, I'm not really surprised about the 2 transformators and the 2 fuses. Oh, the smell here is old electronics. Oy, oy, oy. It is because of the patice PCBs. Oh my god, they smell. I need to open a window really. This is crazy. Oh, the wires here, they are made really, really beautiful. Look at that. Even bent to nice shapes. Wires coming out really, really cute. This is just super, super nice. So all the PCBs there are in some sort of sockets, so you can pull these out to each side. So that means we need to take off the entire cover, but it looks like the case is possible to, yeah, it is still stable without this on. What have we down here? More. Okay, that will be the displays. Oh, with some hand soldered wires. They forgot some tracks or some modification. And there's a, what is that? A proto board with some upgrade in the middle. That is cute. And so this is the high voltage output. Maybe this is a current protection diode or a fuse. It seems to be very loose here. There's a connector. High voltage. This is maybe a double or a triple or something. And then there is the high voltage parts. There's an IC missing in this socket. Maybe that is not a good sign. Maybe it's not working, or maybe... Okay, let's take off the entire top. So to take off, this is just done the most crazy way. It is folding around the bottom part in one piece, and then it sticks down in the front all the way around, and it's like biting really good. There's just no way I can pull this up because of the way that it's, you know, sticks or fits all the way around. And also, you know, here on the sides it's just grabbing. So I'm just trying to see how mean do I need to be here, and how much, when can I pull this way. And I really don't want to screw it up too much, because what if I find out that I can use this for something funny? Maybe I want to put it back together. It's not always stuff goes to trash when it goes through teardown. It turns out that those are not just the rubber feet holders. No. It's the perfect tool to stick in here this way and then do the crack it open. Also, it was perfect to stick in here and then crack it this way when I needed to pull from this side. Also, I had to bend this out a lot and then pull it up. Then I could take it off. It turns out that all the 4 boards, see, they are so loose in the sockets, they just fell out all by themselves. Let's take them out one by one and have a look. Hey, the smell is really crazy. Wow, look at that component. This is an optocoupler, I guess. Yeah. Or maybe it's one with a little bulb in them. Tesla. Those are really nice. Have to look a little bit more carefully into what these parts are. So yes, this is a double-sided. Don't you just love the way that those tracks are routed? Oh, look at that. Oh, look at those 2 tracks. What is this? Why would you do it that bad? It is because this is tape and film. So all this is designed manually, tape and film. Otherwise you would never make it like that. So if we look at one side, the power supplies here are exactly the same. It's also the same PCB layout with exactly the same name and number. They just didn't drill the holes and populate the rest of the parts they need for this unit. But for the other unit, they needed all the parts. See, if we look at them side by side, they're identical. So this is the high voltage supply with all the triple stuff is scooped in. It's really nicely made. So there's a little connector here with good creepage distance, all done in epoxy or something. And this is the high voltage transformator. And I guess this will be the transistor for the transformator and the flyback diode and stuff. Current sense. Oh, look at all the trimmers. But I'm a little bit worried about this IC missing. That is a little bit bad. So that means I can't power this up. Because look, it must be doing something important. I got no clue what it is. There's a lot of poking around with changing features or design bugs, maybe. Let's look a little bit at the power supply board. How do you like this fuse upgrade? It is plus minus 5 volt. And look at the date code, 87. And plus minus 15 volts, and again 87. I really like the detail on the resistors. Of course they put the values up. And they've done this on all of them. Even if we take a look at the other boards, you can always see the resistor values. That is pretty neat. So they did pay quite a lot of attention to detail. Look at all those resistors with the numbers. It's just fantastic. And it's the same with this one. I really don't know those kinds of resistors. See, a lot of them, they are blue and green, but they're exactly the same physical size. Tantalum. Tesla ICs as well. This one is also a Tesla IC. No date codes on those, at least that I can understand what is written on. Maybe those are, I don't know. Maybe this is the reason for throwing this out in the first place. This is the high voltage output. It is broken here. And they use the softest silicon and they glued it with silicon. So there's no relief in the wire. And it was soldered here, but it broke. So this is not how you want to do it. You want to hold this wire so it's not going to break. Look at those super good solderings. Okay, they are kind of connected. What is that? Tiny pieces of metal? So, why all the PCBs, they were out of the sockets? Of course, they've been throwing around with this. Maybe just threw it in the trash can. But there is nothing preventing the boards from going out of the sockets. See, this is the side of the case, and they can all move all the way out. And see, if I just pull this a little bit, it really doesn't take much. So now it's completely out of the socket, and then there isn't really a lot of force needed to operate this switch here, this connector. No. So that means the weight of the board will just be enough to pull it out when this one is dropped on the side. That is not so good designed. Let's look at the back side of the display boards. Look at all those manually cut and added wires. And it is the same on the other one. Funny, there are two different colors, the PCBs. Maybe this is intentionally. But this reveals how big a problem manual designed PCBs really is, right? So this is done way before CAD. So if there was a design bug, all you had to do is cut and wire, and then months of rethinking and redrawing instead of using CAD. Yeah, but this is old stuff. 86 or 87. It maybe took a few years to design this, so it's maybe designed in 85. But I think you had CAD, but not at all like we see it today. I'm still in the should I power this up or should I not? Because there is an IC missing right there. I'm a little bit worried this is doing the voltage control or voltage monitoring of the high voltage. But what can happen? Here we go on the two transformators. It's easier to see on this side here. They added filters on each of them, and the mains is running in shielded, a braid shield that is connected to the chassis. That is really cute. This is because some of this is maybe very sensitive. And there's another transistor regulator, something here on the back. Big TO3. And then the wires for that transistor go in parallel with wires directly from the transformator. That is a very unlogical way to design this. If stuff here is really critical for hum or noise and whatnot from mains, and you put braided shield on your mains wires, why do you parallel with the this is a little bit weird, because those wires, they go to the rectifiers, so that means they carry peak currents. And look at the size of those. They can do like 200 watts each. So, but where are the 200 watts in this thing? I don't know. Maybe this is the high voltage output or the other power supply. Is it really that powerful? I don't believe it. This tiny little high voltage thing is only a few watts. I am probably going to hell for this, for showing you guys bad manners. But I don't have this sort of power supply connector, so I figured, let's see, will it fit? Oh, come on, man! I need to go and cut some more. Damn it! So both of the outputs isolated from the chassis, and one output, I think this is the low output. We got some diodes on the ground, and it goes to the ground of the high voltage output, and then there's a like the high voltage 0 output, and then from this point there is a wire down to chassis. So I think it's just DC outputs, isn't it? So why would you isolate all this? Why couldn't you just have your ground star point here? Because it doesn't matter where it is, right? Just as long as it's so, then you didn't need the isolation. Well. Also, both fuses, they look like they're okay. It's written on the back 0.3 amps. They put in 0.25 amps. I gave up on the connector. So this is not how you want to do it, but we just want to see what happens, won't we? So 221. This unit is designed for 220, it says on the back. Yeah, we're gonna video this. Nothing happens. And that's a good thing, because which one did push first? This one? That one? Yeah, that one. Are you ready? What the heck? Minus 14 what? Minus 14 bananas? Oh, this one. Hello. I don't see anything happening here. Ah, the over. Milliamps. Ah, so there's a load somewhere. So this is volts, and that will be milliamps. The LED is not working. Crap. So high, low. Well, it's alive. Sort of. But I think this is the problem, right? There's even a little bit of light in the red one. Okay, it's 8 watts. And then 0. Alright, no smoke, no kaboom. Let's do this one, okay? I am a little bit scared about what's gonna happen now. 27, okay, 13, 14, 10, 9, 10 watts. Okay, so I'm not so scared anymore. Phew, that was better. Internal. Ooh! Something is happening. So is this accelerating potential of 1 gigawatts? I will measure what is coming out of this thing. Microamps. Ooh. I think we'll start to measure something. So this is what I came up with. The 2 potentiometers here for low and high. That is actually low voltage, or like a negative output voltage, and a high. The high is the positive output voltage. So if we turn this on, it is always in negative output, and it is full negative no matter what we do on the potentiometers. And there is a low and high selector that selects between the preset output positive or negative voltage. So I measured on the 2 potentiometers. There's a positive 0 to 5 volt on this potentiometer. That works. Negative 0 to 5 volt on that potentiometers. That goes to the golden Tesla chip here. And there's also a pin that goes high and low when you select on the low and the high button here. And the output of this Tesla chip goes positive and negative, and is directly connected to these two when I switch the 2 different. So that means it is an analog switch, and it works. So that signal goes to the next chip, and all other pins of that chip is completely unaffected by this positive or negative 5 volts. They're all clamped to their fixed voltages and no changes whatsoever. So I'm completely positive the next chip is the problem. So let's have a closer look at all this that I just said. The 2 input voltage from the potentiometer, and this one is the signal that goes high and low when you push the selector, and this is the output signal that goes high and low. So it goes into this chip. So this pin goes high and low correctly, positive and negative. All other pins are just completely dead. They're just whatever voltage they are. They're not moving at all. So this is the fantastic analog multiplexer, and this is the first op amp, and this is how I trace the signals. Where are we? Here we are. So the 2 potentiometer signals, the analog output signal goes to this op amp, and nothing comes out. So it gotta be that one. The MAC 155 is of course an op amp. It is a J-fed op amp capable of plus minus 22 volts, but we have 15 here. So it should be fairly easy to find another op amp and put in and see if it's working. I think I'll put in a socket, and maybe I'll put this signal at around 0 volts using a voltage divider in the socket first and see if I get 0 volts output. This way I prove that nothing else is dead and there's nothing overloading the output of the op amp, because that could also be the reason for this op amp not to work. So since the output is connected to both 2 and 6, it should be super easy just to mount 2 resistors of same value from the positive and the negative. That means I will have 0 volts, right? And then the output should be 0. Let's see how that works out. So look at the output transistors, an NP and an PNP, just a normal emitter follower. Why would you put that track that close? Not so smart. And of course it is working. It is really, really funny the way that this is operating. So you change between high, that is a positive voltage, and when you want to go negative, it's another pot meter where you set the negative. It is a little bit funny, but this is just the way it is. And so what you're adjusting here is a constant current level. So to get this working, of course you need to load the output with a resistor. So I just put in 1K because that is easy for me to translate the voltage directly to milliamps with a 1K resistor, right? So it is connected to the output, and I am monitoring with a scope the output and the control voltage after the analog selector. So that means we are in the negative. Here we see the gain, and then I can switch to the high and use the other knob to get the high output. So far so good. But there is one other defect with this one. Now I am measuring the output voltage, but now I'm measuring the output current. Also, there's a missing LED here. I guess this has something to do with the voltage or current measurement system. And of course, somebody overloaded it or connected something bad into it so that they killed the op amps. I found that you can just put in LM318. They're pin compatible. I removed the two trimmers because they only do bad things. And I resoldered all the resistors and everything on both sides because I was worried about the old components here. So it's in internal, we are in kilovolts. Let's power it up. Remember, this is kilovolts, so we have to be careful. Ooh, look at that, huh? I am actually amazed it is that accurate. Whoa. So I got 200 volts and that is 0.2 kilovolts. Amazing. Okay, I know this meter goes to like 1,000 or something, right? So just to prove the point, should be able to do that, shouldn't we? Or let's just stop the experiment and see what is the limit on this one without anything connected. We're not gonna blow stuff up, are we? Oh yeah, this is 10 mega ohm, right? So 61 microamps. Oh, that is fantastic. It was reading 0 without anything connected. So the amp meter here works. Whoa, happy. And now the meter is not connected, so we can play. Let's make some kilovolts. Yeah. Well, there is actually a little bit with the pot meter. So 4.7 is the maximum. Nothing is connected. The amp meter works. No, I'm not giving up that easy. Again, this is the 1K resistor, the output, and I got a voltmeter now on that one. So that means 10 volts is 10 milliamps. It is that easy, right? So now I made the amp meter work. So positive and negative. But why is it reading like almost 8 or 7 point something. Volts is almost right. Minus 10.3, it is minus 10 point something, and then high is 10 again. So it's the same. So the voltmeter reads a little bit too much, but the ammeter reads a lot too little. Why is that? And also this LED is annoying. And over? How much is over? This is something I need to figure out, because I just can't find a manual or anything. Haha, I think I found the pot meter for the voltage adjustments. And of course there's another one right next to it for the current. However, when it's maxed, I can't make it read more than this. So that is a little bit odd. Maybe there's a resistor that was also blown, because how can you blow up all those op amps and everything? So I think they made a flash over between the high voltage and this the cathode control. So I think they also blew up the current sense, or the series for the current sense, or that op amp that is doing that. But how can it work if it's the op amp? Nah. Okay, there's also an offset problem. So when I have 0, so that means the amp meter is having some difficulties. Right, how about the voltmeter? Yeah, that voltmeter goes all the way. So that means there's no problems. And of course I would expect a crossover problem. So it cannot make exactly 0, but it can make small voltages. Okay, so that's fine. But current is a little bit off. Ooh, so if you give it a lot of current, what happens when you continue? There is definitely something with this op amp. Look at that. Why would it do that? Is this also a problem in the high? All right, I think I found the bug in the current readout. Because the plus and minus 5 volt supplies for the 2 potentiometers is very close to 5 volts, a little bit over 5 volts actually, just like the 5 volt plus minus 5 volt from the power supply. I didn't give it a lot of extra thought where it was actually coming from. So I just thought, okay, they're just using voltage from a 58 and a 59 regulator as the reference voltages, but no, this is not what they do. They're using a MAC 01. That is a 10.00 volt reference, and it does generate 10.00 volts, this reference. So this reference goes to a MAC 155 op amp. It is coupled as an inverter, so it will make the plus 10 to minus 10 volts. And then with the voltage dividers here, they actually modified the values. So this is the 5 point a little bit and a 5 point a little bit plus and minus going to the 2 potentiometers. So this is nice and stable, and that means when you set up the wanted current, it's going to be absolutely stable and accurate. Fantastic. So I think we could call it a quit. Just accept this LED that is bothering me a little bit, but I think voltage is okay. High. You see, it works. I think this is good enough. The milliamps. This one reads a little bit less. That is a little bit funny. So it's not completely linear, the display at the very low levels. It is a little bit unlinear, so that means this is something I cannot fix. You see, it reads a little bit too much when it's negative, and a little so that's a little bit odd. What I've done, let's pull out the PCB. Also, I made the adjustments accessible from the top when everything is running. Originally, the trimmers, they were on the top and they were only accessed from this side. That means there's no way you can trim this when the PCB is inside the unit, which is a stupid way to design stuff. Of course you must be able to trim from an accessible angle. So I moved the trimmers like this and glued them with the 3D printing resin. Super easy way to do it. Well, it's maybe not the most beautiful solderings, but it is working. So I am in the front. It was actually not that difficult to take out. It was just the 4 screws here off with the buttons, and then everything comes out. It was pretty neat. And this is the frame they just bent and assembled neatly. The fun thing about the 2 display units, they are actually the same layout, but again, just different population of components. Also the microcontroller, what is that? I have not seen that before. And again, the Mag 01 10 volt reference chip. And there's also one here. So this is a 2-layer board, but it is home etched. So there are no VS. They make the VS by sticking through a little piece of wire and then soldering it at both sides, and all the traces that need connection, they solder on the top like that. So I also found out why this LED was not working, and it's because, see, it can move. So there's a bad soldering, and when I move this, it lights up. When I pulled off the front, this the over LED was kind of stuck in the front, and it got off both solder joints. So it's really bad to have holes in the front that's more or less too small for the LEDs. So they could just stick in here and get stuck. So what I did is I drilled all the holes 5.5 instead of 4.9. So they were not so stuck anymore. And now I'm gonna repair the over LED. Also the on LEDs, there are, you can even see how much they were pushed and pressed through the hole. So they were stuck in the hole. Also, if you see those LEDs, look at the marking from the casting, and even the assembly of the 2 halves is done really bad. Very visible in the front, in the middle. I just can't get this shit to focus. Here you can see it. Anybody knows what that means? I got no clue. Maybe it means the super duper good software ready for release. I don't know. Oh, by the way, look at this solder job here. So this is the via, homemade via going through. And it is not short circuiting. Well, I don't know. So now you know why there are all those many wires in all sorts of directions. They're trying to repair all the missing connections in this PCB. That must be the explanation. So, I mean, there's got to be a prototype. How many can you make with all this, redoing this and redoing that, cutting out the holes by hand, and then the other one, oh, I don't need that hole here, I need it somewhere else. It's clearly a prototype or a very, very expensive way to do stuff. Also, if you noticed, the alignments of tracks from one side to another one is done poorly, and it's manually drilled. So this is the kind of alignment you got. Whoa. Can't even remember if I made it that bad. And the holes for the switches, they're almost in the middle. Yeah, okay, cool. I don't know. But I actually think the switches operates a little bit better now when they are not in the front. So that means because of the alignments of switches and because of the two small holes here, they're kind of biting. So I think that is also one of the mechanical problems about how well the buttons they operate, because they really work. What happened here? I kind of didn't ask you to do that, did I? So I was operating them, and then that click. Yeah, okay. It's not going to stay in. Ah, it's because this one is not staying in. Yeah, now it is. Yeah. Not too well.